Let's now talk about perennial favorite, black holes. And first, we'll talk about black holes in general and stellar black holes, then we'll turn to their bigger cousins. This is one slide condensed version of general theory of relativity. As you probably know, Einstein first came up with special relativity, which postulated that all inertial observers are equal, and then came up with Lorentz transformations and E equals mc squared and whatnot. General theory says that all frames of references must be equivalent. Gravitational mass, inertial mass must be the same. And when you work all this through, one important consequence, the most important consequence, is essentially described here. Presence of mass, or energy for that matter, changes the geometry of space-time around them, induces curvature of space. Now, usually we have this two-dimensional rubber sheet analogy, but you can imagine the same thing in 3D. And this is a unique prediction of general relativity, that this will happen. So, general theory of relativity in one tweet is this, that mass changes the geometry of space, and space changes where the mass moves. And if you can solve that in a consistent fashion, that's what Einstein's equations are, you got yourself a theory. So, this was obviously the way to test it. And Einstein figured this one out very early on, but World War I was kind of going on, and that's not the best time to do astrophysics. But right after that, Eddington and collaborators went to expeditions that they measured positions of stars behind sun during a total eclipse, compare those with plates of the same part of the sky taken some other time, and compare the positions of stars. And if the general relativity was right, you will see stars move out a little bit. Because see, the geometry is if the light ray has been bent and you extrapolate it backwards, your extrapolation would miss the actual source. This is behind gravitational lensing as well. And sure enough, they found the value that maximum displacement was a little shy of 2 arc seconds, which was not an easy thing to measure with photographic plates back then. And then this has been, of course, vastly improved since then. But this was seen as a very clean-cut demonstration the theory was actually correct. And this is where Einstein really became famous. Okay, so black holes. Now, simple Newtonian gravity, right? If you have a mass particle, you want it to escape the gravitational pull of, say, planet Earth, you have to toss it with a high speed. Such a high speed that its kinetic energy overcomes the potential energy. And so there is a value of critical velocity called escape velocity. And if you shoot the thing faster than that, you'll have enough kinetic energy to escape. Otherwise, it's going to fall back. Now, the formula is very simple. And so for a given mass, you can make radius smaller and velocity will go up. Or for a given radius, you have to add more mass, velocity will go up. So now if you have a big massive star and you don't get rid of most of the mass from the collapsing core, now shrink the core sufficiently, there is a point in which this escape speed reaches the speed of light. And from that point onward, nothing can escape the collapsing core. So that region of the space is called a black hole. If you actually follow up this simple algebra, you'll get answer that's wrong by a factor of 2, and that's because there are some relativistic corrections, but intuitively it's the exact same thing. So black holes are very simple. There is a point and there is a sphere, at least if they're not rotating. So as far as gravitational collapse is concerned, it keeps going and going and going until the whole thing is condensed into a single point, which then has finite mass and therefore infinite density and infinite gravitational pull. That's called singularity. Now, in reality, who knows what really happens? I mean, at some point, quantum gravity effects must come into play, something else. But in any case, mass gets to be squeezed into a really, really small region. This is not the event horizon. Event horizon is just a surface in space. It's not like a crust of any kind. It's a surface in space at which the escape speed reaches speed of light. So if you're not rotating the black hole, the radius of that is given by this quantity called Schwarzschild radius, which for our sun is 3 kilometers. So for Earth would be 9 millimeters. So you were to squeeze Earth to a pebble size, it will be a black hole. Any mass, no matter how small or how big, can become a black hole if you fulfill this relationship. And since, notice that this radius is proportional to the mass. So what do you think will be the behavior of density with mass? Are the more massive black holes denser or less dense? Well, the density is mass divided by cube of size. So divide both sides of this equation by cube of radius. You get the density on the right side, and you get 1 over radius squared on the other side. And since radius is proportional to mass, density is inversely proportional to the square of the mass. More massive black holes have lower densities. And actually, if you were to look at the black hole that is size of the universe, the density inside would match the one that we observe in cosmology. So we could be living inside a gigantic black hole. If the black hole spins, things get a little more complicated, but don't need to go into that. And the only other thing you can possibly know about black hole is electric charge. But since positive and negative charges seem to be mixed very well, usually that's not important. And since you only know 3 numbers, it doesn't matter what black hole is made of. Stars, gas, dark matter, pineapples, cars, TV sets. It doesn't matter as long as it has a mass. That means that information about building material has been destroyed. So black holes are the biggest generators of entropy in the universe, by far, because you have vast amount of information describing all the material that was going to fall in, and then 3 numbers in the end. Well, effectively 2. If they have entropy, then they might actually have temperature, and they do. I'll come to that in the end. But here is the interesting thing. This is a completely fake artist impression, just trying to indicate that there is somehow a hole in the space-time. Interesting things happen. As you fall towards event horizon, the clocks slow down. There is slowdown of clocks as you approach in higher gravitational field. And in fact, if you look from far away, the time stops at the event horizon. And things that fall into black hole actually never fall into black hole. They just get squished right before event horizon, forever. However, for the astronaut that's jumping into black hole, nothing happens. It just goes through the surface, doesn't notice, and, well, might get stretched by infinitesimal forces, but aside from that inconvenience, it takes a finite amount of time to fall all the way down into singularity. So different observers, one far away, one actually dipping in. For one of them, this is a finite duration of time. For the other one, it's infinite. Well, this is why it took Albert Einstein to figure this one out. So how do we make them? Well, it's, again same thing as making of neutron stars. This time, the equivalent of Chandrasekhar mass is 3 solar masses. It's actually called Oppenheimer-Volkov limit, and it corresponds to the degenerate pressure of neutrons instead of electrons. So if you have core that's less than 3 solar masses, you can arrest collapse, have a big neutron star. More than that, nothing can help. It just has to go through a complete gravitational collapse. And so that point in the middle, as I said, it's called singularity, because some physical values reach infinity, which of course never happens in reality, but that's the math, right? And that finite volume around it within event horizon, which is the surface at which escape speed is equal to speed of light, that's a black hole. Okay, so how do we know such things exist? Well, just like with X-ray binaries, you had a dense companion, white dwarf, some stuff falling from companion star, converting its binding energy into kinetic energy, comes to a stop in the middle, radiates away that kinetic energy. Put a neutron star, you're going to get even more spectacular version of the same thing. Put in a black hole, same thing will happen. You get even more spectacular conversion of binding energy into first kinetic energy and then radiation. And generic expectation was that material that stops right shy of black hole will be shining in X-rays, just like with neutron star binaries, but there is a way to tell, because you may remember that for neutron star binaries there are pulses. And if you see X-ray binary with the right kind of properties and doesn't pulse, then chances are it's powered by a black hole. Very famous one is called Cygnus X1. And in some cases, if there is magnetic field that was left over that can accelerate particles, again, just like pulsar, except this time, this is a black hole and tends to be well aligned with rotation axis. Those are called microquasars. So those are pretty spectacular objects. In fact, there's more spectacular objects inside our galaxy on stellar scale. But the really spectacular ones are those that are on galactic scales. So one last thing about black holes, and this is Hawking radiation. So remember I told you that black hole generates a considerable amount of entropy, but it also has a temperature. And it works like this. In quantum physics, we believe, and there are excellent experimental reasons to believe this, that physical vacuum is constantly bubbling, creating particle-antiparticle pairs, but they annihilate within the interval given by the Heisenberg's uncertainty principle, so that normally you never see anything. But what happens if you do this just outside the event horizon, and it's an electron-positron pair? Well, one of them falls in a black hole. Then the other one remains free, looks for some other partner, annihilates with that, but they're doing this outside the black hole, and so that radiation can escape. I mean, this is a little more complicated, but that's the basic idea. And so black hole radiates by sucking up one half of these virtual particle pairs. The others are annihilating. That energy has to come out of somewhere. It comes out of the rest mass energy of a black hole. And so they have temperature, they have luminosity, and they have entropy and a lot of thermodynamical quantities, and they're the most perfect black bodies, and this is no pun, ever. Now, nobody's ever actually observed this. This is purely theoretical construct, but it's a pretty convincing one. Now, interesting thing about this is that the temperature of a black body black hole is inversely proportional to its mass. The smaller ones are hotter and therefore radiate faster. And so the rate of evaporation accelerates in time as you go to a smaller mass, gets hotter, lose more mass, and so on. And in the end, there is like a flare, and black hole is gone. If you ask yourself the question, how long does it take? You can compute that formula and match that to age of the universe. You find out that those are some pretty small black holes. So the ones that we know about, this like stellar black holes or galactic ones, they'll last a long, long, long time. So we won't be able to observe this.